Hello everyone, I'm Aryansh Vasu and this is my presentation for PHN 315 Signals and Systems. And my topic for today's presentation is edge detection in image processing using convolutional filters. Let's take a look at what is edge detection. Edge detection is the process of measuring the sharp changes in the image brightness. It is useful for feature detection and extraction and is used in image processing, machine learning, and computer vision. It is also used to achieve stylized effect in video games and 3D engines. So the objective of this presentation will be to find the system which, when given an image as an input, will give an output image with the edge information. The output of an image can be calculated by convolution of the input image with the impulse response of the system, which is nothing but the output of the system when the given input is an impulse. Let's take a look at what is convolution. Convolution is an operation on two signals that expresses the overlap between the two. The continuous time convolution of between two signals fx and gx is defined as such. In discrete time signals, convolution can be thought of as flipping one signal and then shifting it and taking the dot product of the two signals, which is just multiplying the corresponding signals and adding each one. For example, let's take a look at what will be the convolution of two signals 1, 2, 3 and 4, 5, 6. So let's flip the second signal 4, 5, 6. We'll then shift the second signal and we'll multiply the corresponding terms. 1 times 4 will give 4. We'll then shift it and then we'll multiply and add each term. 1 times 5 plus 2 times 4 will give 13. We'll shift it again and we get 28. We'll shift it again to get 27 and again to get 18. If we shift it further, we'll get 0. Hence, we can imagine that there are infinite number of zeros on either side of our output. For a 2D image, convolution is similar, but instead of shifting in one direction, we have to shift in two directions. Hence, our output will also be a 2D array. Now let's take a look at edge detection filters. A filter is just a signal with which our input signal is convoluted with. It is often also called a kernel. Our job is to find a filter that can give the desired result with edge information. There can be multiple filters and methods that can highlight edges. We'll be discussing some of them in this presentation. First, let's take a look at the gradient filter. Since we want to measure sharp changes in the intensity, the gradient comes to our mind, as the region with the large changes in intensity will have a large first derivative, and region with no change will have zero first derivative. For example, let's take a look at the image on the left. We can expect to have an edge on either side of the black band. If you observe the intensity across this red line, we'll see that it's 1 and then it goes to 0 and then it goes back to 1. If we try to find the first derivative of this signal, we'll get 0 and then we'll have a negative first derivative and then it will be 0 again and we'll have some positive first derivative and 0 again. Hence we can see that maxima in first derivative can correspond to an edge in our image. As discussed earlier, we are interested in the impulse response of our system. The output of a differentiator can be written as such. If we provide the input as an impulse, we'll get this output. If we put the value of n as -1, 0, and 1, we'll get 1 by 2, 0, and -1 by 2. We can ignore the scalar factor and hence we'll get our output as 1, 0, and -1. And this will be our filter. Thus, we have obtained the partial derivative with respect to x. However, this will only give the edges along the x direction. We also need to use the partial derivative with respect to y to get the edges along the y direction. For that, we'll use this filter, 1, 0, and -1. As we can see, taking partial derivative along x gives edges in along x direction, and taking partial derivative along y gives highlights edges in y direction. There are some limitation of using gradient filter, and some modifications are made to it to get better results. A commonly used version of the gradient filter is the Sobel filter, which is given as such. There are other filters such as Prewitt filters. Now, it is a common practice to add both partial derivatives and then threshold the values such that values above a particular threshold are assigned 1 or white, and values below the threshold are assigned as 0 or black. Now let's take a look at the Laplace filter. It is another filter which is used to compute. It is a filter which is used to compute the second partial derivative of the image mathematically if it is defined as such. If you try to solve this, we'll get this result. If we provide an impulse as its input and we try to solve it as we did for the gradient filter, we can get the impulse response of a Laplacian. If we do that, we'll get this filter known as Laplacian filter. Note that this filter is opposite in sign of the one obtained by the previous equation. However, this is more commonly used and more straightforward. Now, these filters are quite sensitive to noise, so it's a common practice to smooth the image using a Gaussian filter to suppress high frequencies before convolving it with the edge detection filter. Now let's take a look at the Gaussian filter. It is a low-pass filter. What it does is that it takes the weighted average of the pixel values, with the pixel closer to the central pixel having higher weight and pixels further from the center having lower weight. The weight of each pixel follows a Gaussian distribution. As we can see, the central pixel has greater weight and the pixel away from the center has lower weight. They are calculated from this equation, which is a Gaussian function. Here, sigma controls the amount of blur. Greater the sigma, the more the blur will be. Now, surprisingly, Gaussian filter can also be used to detect edges. By convolving an image with two Gaussian filters with standard deviation as sigma and k sigma, where k is just a scalar factor, and then taking the difference, we can get effective edges. This filter is known as difference of Gaussian. As we can see, we blurred the image twice and then we subtracted the second image from the first, and then we can get effective edges. Now, let's take a look at how these filters will look like in practice. Here we have a Python implementation of our filters using OpenCV. First, we'll load our image and set up some parameters. Then, we'll declare our filters, which are nothing but 2D arrays. Then we'll calculate our convolution, and then we'll threshold our images. And here we are just simply showing our images. Let's try to run this code. So as you can see, this was our original image, and this is after the convolution with our gradient filter, and this is after thresholding it. This is for a Sobel filter instead of gradient filter. This one is for our Laplace filter, and this one is for difference of Gaussian. With that, I would like to conclude my presentation. Thank you very much for watching.